today's lecture, we will be covering part 2 of chapter 12 on alcohols and phenols. So a diol is going to be a alcohol that contains multiple alcohol functional groups within the molecule, specifically two. The most common diol is ethylene glycol. This is antifreeze, a compound you may all be familiar with. And there are a variety of different types of diols depending on the carbon chain length, but particularly any alkane that has two alcohol functional groups within it is going to be a diol. And we can also use a glycol to describe a diol. There are a few methods to prepare diols that we've already learned. Um, Specifically, the reduction, all three of the methods of reduction can be used to prepare diols if there are two ketones or carboxylic acids in the starting material. So in this example here, we have a 1,5-diketone, and under any of these reduction conditions, we would convert it to the diol. In chapter 9, when we were looking at the addition reactions to alkenes, there was a few sets of conditions that gave us either the anti or the syn dihydroxylation to form the diol. So this forms a 1,2 diol. But now we're going to look at probably one of the most powerful and useful reactions in organic chemistry. And this reaction is called the Grignard reaction. Um, it's going to be used to synthesize alcohols, and it also is used to form a carbon-carbon bond. So, I've always highlighted for you the carbon-carbon bond forming reactions that we've learned, and up until this point we've just learned a couple. But this is probably the most utilized and the best way to form carbon-carbon bonds that we're going to look at this semester. So pay close attention to this reaction. In the Grignard reaction, we're going to take an alkyl halide, such as an alkyl chloride or an alkyl bromide, and treat it with magnesium metal. The magnesium metal is going to insert itself between the carbon and the halogen. So for example, if we take bromobenzene and treat it with magnesium, then we would get out this Grignard reagent. So the reagent that has the magnesium carbon bond is called the Grignard reagent. And if we take this propyl chloride and react it with magnesium, we would get out this Grignard reagent. And we can then use these Grignard reagents as a nucleophile. These are a source of carbon minus. If you look at the electronegativity of carbon and magnesium, it highly favors carbon. So carbon's going to be extremely greedy when it comes to the electrons of this bond, and it's almost like an ionic bond. It has significant ionic character, therefore we'll have a partial negative charge on the carbon and a partial positive charge on the magnesium, or you can almost think of it like a carbanion. Um, and this makes it a strong base and a strong nucleophile. And up until this point, we've seen many, many examples of carbon with positive charge on it, but it's kind of rare that we actually see an example of carbon with a negative charge on it. So this is a way to access carbon with a negative charge on it. A couple other ways that we've seen to do this are using the cyanide ion. That is a with one carbon with a negative charge on it. Also, we can deprotonate an alkyne. That's the other form of carbon with a negative charge. So this is the third variation of carbon that has a negative charge on it. And the nice thing about this is we can use it to form carbon anions of all sizes. We can use it to form really small building blocks with carbon negative, and we can use it to form really big building blocks with carbon negative. And this provides us a carbon that is a strong nucleophile as well as a strong base. So we can look at the mechanism of how a Grignard reagent will react. And this is actually a mechanism that's very similar to one you've already seen. It's going to be very similar to lithium aluminum hydride attacking a carbonyl compound. instead of the hydride with the negative charge, the hydrogen with the negative charge, we're going to have the alkyl group with the negative charge. And that's going to do a nucleophilic attack on the positively charged, partial positively charged carbon of the carbonyl. And then the bond breaking will be the carbon-oxygen pi bond. Those electrons go up to the oxygen, and we formed our new carbon-carbon bond. And then in the second step, we will have a proton transfer, which liberates the alcohol. So the key difference between this and the lithium aluminum hydride reaction is obviously that we form a new carbon-carbon bond. Now, the Grignard reagent is actually tricky to use in the lab, especially in Florida, and that's because it's also a strong base. So even though we want it to form a reaction with the carbonyl carbon, if there's any water around, it's going to deprotonate the water, and that's going to ruin the Grignard reagent. So we need to make sure that any solvent we use for the reaction is completely anhydrous, and ethers are generally uh, really good at staying anhydrous. They don't pull in much water from the atmosphere. So, and especially in Florida, where we have really high humidity, we're going to want to make sure our solvents have as little water in them as possible, because any molecule of water that's in the solvent is going to ruin a molecule of the Grignard reagent before we have a chance for it to react with the carbon of the carbonyl compound. So we'll often use ether or tetrahydrofuran as a reagent. And so here are a few examples of Grignard reagents. If we take this ketone with methyl Grignard, we're going to form a new carbon-carbon bond at the carbonyl carbon, and that also creates an alcohol. If we take this butylaldehyde and have a Grignard reagent attack, then we would form a new carbon-carbon bond. Now, here's another example. Here we have an ester instead of a ketone or an aldehyde. So this carbon is in a higher oxidation state. Remember we talked about oxidation states on Thursday. This carbon is in an even higher oxidation state, and it's able to make two full additions, and therefore we're going to get a tertiary carbon, tertiary alcohol as our product. And this is similar to the LAH reduction again. If we use LAH on an ester, we would also have two new bonds formed with the hydrogen, but in this case, we're forming two carbon bonds. So let's take a look at this starting material here. On this starting material, we have on one side a bromine, and on one side we have an alcohol. So if we want to go form a Grignard reagent, we would hypothesize that we would form the magnesium carbon bond over here because that's where the halogen is. But there is a problem here, and that's because we have an acidic proton on this oxygen. And remember, the Grignard reagent will not work in the presence of an acidic alcohol because it will react with the negative charged carbon and ruin the Grignard reagent. So before we use any substrate for a Grignard reaction, we're going to have to make sure that there are no acidic protons on the substrate. This can be a little tricky because maybe we do want our substrate or our starting material to have acidic protons in it eventually. And so this is going to introduce the concept of a protecting group. So what we can do is use a protecting group on the alcohol. We can temporarily cap it. You can think of it as taking a marker and putting the cap on the marker so that it's not going to get ink anywhere, right? We don't want this alcohol to react with anything, so we're going to cap it. So we use some sort of protecting group. We convert the alcohol into another functional group that can be easily converted back into an alcohol. So first step, this is a three-step process. The first step, we protect the alcohol. We do a reaction that converts the alcohol to something else. Then we do our Grignard reaction. And then we remove the protecting group, and that liberates the original alcohol. And if this reaction sequence takes you a couple tries to kind of follow the atoms that are reacting here, I would suggest numbering. You can number this as carbon 1, carbon 2, carbon 3, and you can see in carbon 1 goes here, That's where the negative charge on the Grignard would be, forming the positive charge with the ketone in this reaction, and then carbon 1 would end up here, and this alcohol is the original alcohol of the starting material. So probably the most common alcohol protecting group is trimethylsilane. There are a variety of different silane protecting groups, each with different substituents on them. This is the structure of trimethylsilane. It's just a silyl group which has very similar properties to carbon and three methyl groups around it. And so we can protect the alcohol with the silane group using the reagent TMS chloride, so trimethylsilane with the chloride leaving group. This, in the presence of a base, this just does an SN2 reaction, and that will TMS protect the alcohol. And then you get the salt as the byproduct. And this protecting group works just fine if you would like to do a Grignard reaction with your alcohol present and protected. The is much larger than carbon, and so it's easier to do an SN2 reaction on a silane than it is on a carbon. If we tried to use trimethyl carbon chloride or terbutyl chloride in an SN2 reaction, we wouldn't work. We spent all of chapter 7 seeing that this type of reaction would not work. Instead, it would go SN1. But because the silyl group is below carbon on the periodic table, it has similar reactivity, but the size of the atom is just much larger. And to get rid of our TMS group, we can use strong acid or F minus. F minus can come in several forms like hydrofluoric acid, but hydrofluoric acid is extremely toxic and something we want to avoid using. So to get around that, we generally use TBAF, tetrabutyl ammonia fluoride ion, and this is a source of F minus and used as a reagent to deprotect the TMS after we've done whatever chemistry on the substrate that we need to where there is no alcohol. So overall, our process for that reaction that we looked at before would look something like this. We begin by identifying that in order to do a Grignard reagent, we need to protect this alcohol, and we can use TMS chloride and triethylamine to protect it. Then we form the Grignard reagent at this position. Our carbon minus would then be here. By inserting the magnesium, we can then react it with our ketone to form a new carbon bond, this bond here, and then treat it with water to protonate the alcohol, and then finally use TBAF to deprotect the TMS group. So phenol is alcohol attached directly to a benzene ring, and it's a really common precursor for many different molecules that might incorporate a benzene ring, and it's an electron-rich benzene ring. We have the alcohol donating protons into the benzene ring. So here is the industrial synthesis. We take this alkene and phosphoric acid and form a new carbon-carbon bond, which then in the presence of oxygen can form this peroxide, and that then this becomes a leaving group to form phenol and acetone in this rearrangement. Phenol is a precursor for many chemical syntheses, so it's used in pharmaceuticals and polymers, food preservatives, etc. We're going to go through now a slew of different reactions that alcohols are used for as a substrate. That we've kind of ended this portion of the lecture where we're talking about the synthesis of alcohols and the preparation of alcohols, and now we're going to show some useful chemistry that alcohols can be used as a substrate for. Some of these are review, including these first couple here. In the presence of an acid, we can take a tertiary alcohol and form a carbocation, which then can undergo nucleophilic attack. So we can convert it with some alkyl halides to we can convert it to alkyl halides with HCl or HBr. In the presence of a primary or secondary alcohol, we can form these same products, but instead we're going to undergo a different mechanism. We still have a protonation, proton transfer as our first step, and then on the second step, instead of a loss of a leaving group, we have concerted nucleophilic attack of the halide anion to form the product. There are a variety of different ways to convert an alcohol to a alkyl halide. One example, we can use zinc chloride with HCl. So the chloride is going to be a little bit less nucleophilic than the bromide, and in the presence of zinc, we're going to activate this oxygen to make this a better leaving group. And if you look at the mechanism of this, it looks similar to protonating the oxygen, right? We put a positive charge on this oxygen, and that makes this carbon more susceptible to nucleophilic attack in an SN2 reaction because we have a better leaving group here. Overall, alcohols are not good leaving groups, but we do have methods to convert them into good leaving groups. So the reaction we previously learned to do this is taking tosyl chloride in the presence of pyridine. Pyridine acts as a base to deprotonate, and then it does an SN2 reaction with the tosyl chloride to make the tosyl group, and then we can do an SN2 reaction with the tosyl group as a good leaving group and install a halogen, or really any nucleophile at that point. If we do an SN2 reaction on the a alcohol that has a defined stereochemistry, we're going to obtain the inverted stereochemistry in this position. And there are a few reactions that we have where we can convert a primary or secondary alcohol into a halogen, an alkyl halide, the without using the tosyl group as a leaving group. So both of these reactions here have really good mechanisms that I suggest taking a look at. Their mechanisms are unique to this chemistry, so you'll learn a little bit more about how mechanisms work by practicing these, but we can convert a primary alcohol using SOCl2 and pyridine into a primary chloride, and we convert a primary alcohol or secondary alcohol using PBr3 to a bromine. So we could start with the SOCl2 mechanism. To begin with, the oxygen is going to form a bond with the sulfur, breaking the sulfur-oxygen double bond. Then we have this oxygen pi bond reforming and chlorine getting ejected as a leaving group. The pyridine then deprotonates the alcohol, and at this point we have created a good leaving group on the alcohol, on the oxygen of the alcohol. And so chlorine can then do a nucleophilic attack on the carbon attached to the oxygen to form our new chlorine carbon bond, and this gives two byproducts, SO2 and chlorine. PBr3 is going to have a similar mechanism. We begin with oxygen attacking the phosphorus, then the bromine leaves. Now we have created a good leaving group at this point, and the bromine can attack the carbon, which undergoes an SN2 reaction, and the leaving group leaves, and that gives us just one byproduct this time, and our alkyl bromide. A tertiary alcohol can also undergo an elimination reaction in acidic conditions, and we can see that mechanism of this where we have a proton transfer to form a good leaving group, then we'll have a carbocation, and then a molecule of water can deprotonate the beta hydrogen to form the alkene. This reaction is a review from chapter 7. Our elimination reaction is going to have two possibilities for regiochemistry. We can form the more substituted alkene or the less substituted alkene. And if we're going to be doing an E2 reaction, this can be controlled through the use of a bulky base versus a skinny base. This is also review from chapter 7. If we have an alcohol that we're converting it into a good leaving group, then a strong base can be used to push it in the direction of an E2 reaction instead of an E1 reaction. The benefit of pushing it through the E2 mechanism is that we're not going to be forming the carbocation. If we form the carbocation, elimination reactions can occur. In some cases, depending on the product we want these elimination reactions to occur, and in some cases we don't. So really you want to go after the mechanism that you want based on which product you want, which mechanism is going to lead to the structure of the desired product. So we've covered reduction already, converting a carbonyl compound into an alcohol. But the reverse process is also possible, which is oxidation. So we're going from one carbon-oxygen bond to two carbon-oxygen bonds, or we can even oxidize further to three carbon-oxygen bonds or four carbon-oxygen bonds. So in this next segment, we're going to discuss different sets of reagents and conditions to do oxidation reactions. The oxidation state of a carbon depends on what four substituents are attached to it and the relative electronegativities of those substituents compared to carbon. So in a carbon-oxygen bond, the oxygen is hogging most of the electron density. So we can think of it as the oxygen having 2 electrons and the carbon having 0. The more carbon-oxygen bonds we add, the less electron density is around the carbon, and so it is considered oxidized, or a loss of electrons. If we oxidize a secondary alcohol, we're going to form a ketone. If we oxidize a primary alcohol, it can oxidize once up to a aldehyde, and then we have another carbon-hydrogen bond, and it can oxidize further up to a carboxylic acid. What we can't do at this stage is break the carbon-carbon bonds to form carbon-oxygen bonds. That requires a different type of reaction. It requires nucleophilic oxygen and breaking a carbon-carbon bond. So tertiary alcohol, right, with 3 carbons attached to it, if we try to oxidize these under our standard oxidation conditions, we're going to have no reaction because there are no carbon-hydrogen bonds that can be converted into carbon-oxygen bonds. The most commonly used oxidizing agent is chromic acid. Chromic acid, or the Jones reagent, and we can obtain this by taking either chromium trioxide and sulfuric acid, or sodium dichromate and sulfuric acid, and form chromic acid. So the chromic acid is the active oxidizing agent, and chromium, unfortunately, is quite toxic and not very good for the environment. However, this is an extremely productive oxidizing agent. So if we take a alcohol, so here we have a secondary alcohol, and we have Jones reagent, then we're going to form this chromate ester intermediate, and then water can deprotonate the hydrogen attached to the carbon that's being oxidized, and that forms a new carbon-oxygen double bond. So we can use chromic acid to oxidize an alcohol up to an aldehyde, and then a second molecule of chromic acid will oxidize the aldehyde up to the carboxylic acid. In some cases, we might want to just form the aldehyde, and we have a reagent that can do that. PCC, or pyridium chlorochromate, can be used to oxidize an alcohol only up to the aldehyde stage. So just like we have sodium borohydride, which will only reduce an aldehyde or ketone and not a carboxylic acid, we can, using specific reagents, oxidize up to a specific intermediate. So here, primary alcohol in the presence of dichloromethane as a solvent and PCC will generate just the aldehyde. If we have a secondary alcohol, we don't have to worry about over-oxidation because it can only go up to the ketone. It's already forming two bonds with carbon. Those bonds won't be broken. So we can use the Jones conditions or the PCC conditions to convert a secondary alcohol to a ketone. There are alternative oxidation conditions that we can use. As I mentioned before, chromium is extremely toxic and harmful for the environment. So we have alternative mechanisms and sets of reagents that we can use for these oxidations. The first is the Swern oxidation. So the active oxidant for this is going to be an intermediate that is a combination of dimethyl sulfoxide and oxalochloride. To begin with, the dimethyl sulfoxide oxygen acts as a nucleophile, and one of the carbonyls of the acid chloride acts as the electrophile. We form a new oxygen-carbon bond, breaking a carbon-oxygen pi bond. Then the oxygen collapses back down and expels the chloride ion as a leaving group. At this point, we get a 8 electron shift or rearrangement that will result in the formation of the chlorodimethyl ion. And this also liberates a molecule of CO2, a molecule of carbon monoxide, and a chloride ion. Our secondary alcohol can then react with the active oxidant, forming this intermediate, which will then undergo proton transfer, a second proton transfer, and an intramolecular elimination proton transfer and loss of a leaving group process to give a ketone and dimethyl sulfide as a byproduct. So this mechanism is extremely complicated, but there are a lot of really good steps to this mechanism. We have substitution, we have elimination, we have proton transfers, all in the same mechanism. And so it'll culminate in the formation of a ketone that came from a secondary alcohol. In the presence of a primary alcohol, the Swern oxidation conditions will also stop at the aldehyde stage. So we now have two reactions that will convert a primary alcohol into an aldehyde and will not over-oxidize up to the carboxylic acid. The final reaction we're going to look at today for the oxidation is the Des-Martin-Pyrrhonone oxidation. And this will take a primary alcohol to an aldehyde, as well as a secondary alcohol up to a ketone. So we're also able to stop at the aldehyde oxidation state using this reagent. Here's the structure of the reagent. We have this hypervalent iodide with 3 acetates attached to it, and a lactone attached to a benzene ring. So the oxidation for this is going to be a cyclic transition state here, and it'll also form acetic acid as a byproduct. So that as the reaction goes to completion, you can kind of get a whiff of vinegar out of the reaction mixture. So for this reaction, go ahead and take a minute and try to predict the products of this reaction. Using chromic acid, what is going to happen to this substrate? We have a secondary alcohol, a primary alcohol, and an aldehyde all in the starting material. The secondary alcohol can oxidize all the way up to a ketone, the primary alcohol up to a carboxylic acid, and the aldehyde up to a carboxylic acid. And you can repeat this thought process for all of the different reagents that we've looked at using this molecule. If you were to put, for example, DMP here, what type of product would we get? Biological systems also have oxidizing and reducing agents that are used to convert different molecules in your body. And so one of the most common we have is NADH, and this is a reducing agent. It's comprised of a base, adenine, a sugar, and then a diphosphate linkage, another sugar, and then the reactive center here where the chemistry occurs. And the reactive center is a source of hydride. So it's a source of H minus, just like LaH or sodium borohydride were a source of hydride. NADH is a source of hydride. So we can kind of summarize the rest of the molecules in our group for now. And you can see the mechanism of how the hydride's delivered. The nitrogen electrons push through and create, kind of eject this hydride, which will then attack a ketone or an aldehyde, and then another enzyme will protonate the alcohol. And so this is one way in nature that we can convert carbonyl groups to alcohols. The product of NADH doing a reduction is NAD plus, and NAD plus can catalyze is part of the reverse process. In the presence of an enzyme catalyst, it can convert an alcohol up to a ketone, oxidize it up to a ketone. So in nature, we have kind of this this process where we have either NADH or NAD plus converting a molecule of ADP to ATP, and then the citric acid cycle can convert the NAD plus back to the NADH, where we have another reaction that can occur. And this is a key portion of the uh, metabolism and the citric acid cycle, and you'll learn a lot more about this specific cycle in biochemistry. So a tertiary alcohol, right? We learned that we cannot oxidize this up because there's no alpha proton. This carbon is making 3 bonds to carbon and 1 bond to oxygen. And if we compare this to phenol, you might at first think, since there's no beta hydrogen, that we might not be able to there's no alpha hydrogen, so we might not be able to oxidize this, but that's not true. In fact, phenol is even more readily oxidized than primary or secondary alcohol. So we can take a phenol using the Jones conditions and convert the phenol into a benzoquinone, and then this can in turn be either reduced to hydroquinone, or the hydroquinone can be oxidized back up to the benzoquinone. So this conversion between a quinone and a hydroquinone is a key process in cellular respiration, and it allows these benzoquinones to act as an electron sink biologically. So to cap off our alcohol chapter, we're going to think a little bit about synthesis and synthesis strategies. Um, Remember the two main categories we kind of want to look at are changing the carbon skeleton. We've learned a new method for adding carbons, right, using the Grignard reagent, our new source of carbon nucleophile. Some reactions that we've covered so far, we can take an alkyne and reduce it down to an alkene, reduce that down all the way to an alkane, and oxidize back up using a variety of different conditions. And with alcohols, we can do something similar. We have now the ability to oxidize a primary alcohol up to an aldehyde using, I think we went over 3 different sets of conditions that would do this. We also have the ability to reduce the aldehyde back down to an alcohol using a variety of different conditions. We can take a secondary alcohol and convert it to a ketone, and we can reduce this ketone back down to a secondary alcohol. Now the ketone and aldehyde are carbon electrophiles. So we have a carbon with a positive charge, partial positive charge on the carbonyl carbon, and those can undergo a variety of different chemistries. And so we can kind of group these types of conversions together, right? Our alkynes can be reduced to alkenes and alcohols and reduced further down to alkanes, or we can oxidize up. And we can group the 6 functional groups together by their oxidation state, similar to what we did on Thursday. And if we take a look at our spider chart for this, now we have a whole new set of substrates that we have access to, which are the ketones and aldehydes and the alcohols, and you can kind of see where these fit into our broad scheme, right? Really, we can convert our alkynes and our alkenes into alcohols and ketones. We can go through alkyl bromides, and we can go directly from an alcohol to a ketone, and vice versa. And then finally, and probably the most important part of this chapter, the strongest reaction, and the one that we'll have a lot of fun doing in the lab because of the techniques involved, is the Grignard reaction. And this gives us the ability to form new carbon-carbon bonds. So this is extremely powerful reaction. Um, these examples here are just adding one carbon with the methyl Grignard, but we can, remember, instead of this piece here in red, we can have a much larger carbon chain that we're adding to the carbonyl compounds. We don't really have a way to convert an aldehyde directly into a ketone, but through a Grignard reaction, we can grow the carbon chain of an aldehyde by first converting it to an alcohol and then oxidizing it up to the ketone.